Right, this is a lecture on Poincare's lemma and the potential function. So, Poincare's lemma is to do with the potential function. Right, first off, a definition. In order to do the potential function, we have to first determine whether a function is conservative. And to do that, we find out if it's irrational. So, this means that if a function is irrational, then the partial of fi over partial of xj equals partial of fj over partial of xi, where I does not equal j. Now, to make sense of that, I've put this here. So here is f1, f2, f3, so x, y, z. And here is x1, x2, x3. Let's refer to them like that. Then f of f1 over, should we say, x2, so fx over 3y must equal, if we partial them both, fy over x 2x, over 2x. So we've got the 1, 2, 2, 1. I've got an example later which will make much more sense of that if that made no sense. Then to find the potential function for, I can't remember what that's called, I'll call it theta. We have d theta over dx. This goes to theta equals f of x dx, and it's the same for the y's and z's. Yeah? And what is the potential function? Well, it's just a way of writing down a function, really. That's how I imagine it. And we have f of x, y, z equals the gradient vector of the potential function. So we can look at this in the example I've got coming up, which will make sense of that. Right, here's our example. Find if f of x, y, z equals 2x, y, z, x squared z, x squared y. Find if that is conservative. Now first we've got to find if it's irrotational. So what I've done here, I've got, hope you can see that, partial f1 over partial x2. So all we do is we have x over, where's our x2, x squared z. So we're just differentiating x squared z with respect to x, and that will give us 2xz. Yeah? And over here we've got y and dx1, so we want to differentiate 2xyz with respect to y, because we're f2 this time, and that will give us 2xz as well. So that one's worked. Let's change the numbers, so we'll have 1 and 3 this time. So df1, so we want to do x, and partial 3 is x squared y, so differentiate x squared y with respect to x, and we've got 2xy, and f3x1 is f3 z, and x1 is 2xyz. Take off the z because we differentiate with respect to z, and we'll get the 2xy, and it's the same for here as well. I hope that made sense. Right, so what we've actually proved, if we've proved that it's irrotational and hence conservative. Now we want to construct a potential function. So what we've got to do is just use that little thing I did before, which was the d theta over dx equals the x part, which is 2xyz. Then if we rearrange this, you can move the dx up, can't you? And if we just ignore the delta there, we get theta equals 2xyz dx. Yeah, that's pretty straightforward, I think. And so if we integrate that with respect to x, we get x squared yz, plus a constant, if you want to be dead cert. And then we do the same for y, which will give us, which is the x squared z here. Gives us theta equals x squared z dy, because we move the dy up and just leave the theta where it is, kind of. And, well, it is really, because it's 1 d theta, integrate that, never mind. X squared yz, that's again, look, have you noticed they're actually the same? And for the last one, with our d theta dz, it's x squared y, which is this part here, which is theta, equals x squared y dz, integrate that, x squared yz. Now, we've noticed here that they're all the same, and what I've said before in this slide is that you never include the term more than once. The method's not very good, but if you understand how to do it, then it's actually very straightforward. So therefore our function is theta xyz equals x squared yz. If you had it doesn't have to be in all of them, so if you had x squared yz plus x squared on this term only, you'd still have x squared yz but have plus x squared on the end. So you only have to include a term once, but it doesn't have to be in all of them. And as we can look, as I said, sorry for jumping back and forth, we've got grad f is the theta function here. If we look at this here, we can actually show that with our function. If we differentiate this with respect to x, we get this. With respect to y, we get this. With respect to z, we get this. So it is the grad. If you multiply this by grad f, then it will give you the function. So we know that's correct.